Welcome back to what should be our last little video on density, I'm hoping. So let's take a look at our density calculation, and this is how we would determine the density of an irregular object, something that it would be difficult to measure with a ruler or with graduated cylinders, for example, for a liquid. And here's how we would get its volume. So to determine the density, they took the stone. We've got the mass of the stone alone this time, although we could have had a mass of a weighboat, then the mass of the weighboat plus stone, and get it by subtraction. But in this case, what we likely did, and you'll learn this term soon, is we would tare the balance to get rid of the container, and we have the mass of the stone alone. We took a 100 milliliter graduated cylinder, and we added water up to the 45.0 milliliter mark. So we have a mass, let me write that data down first, our mass of 15.25 grams. We have an initial volume in that graduated cylinder of 45.0 milliliters. Now, at this point, what's done is the stone is dropped into the water. This only works for things that don't react with water, by the way. So the stone is dropped into the water, and we have a final volume equal to 50.8 milliliters. Now, the difference between these two is the water displaced. So the change in volume is going to be the water that was displaced by the stone. And that's going to equal the volume of our amethyst. Love amethysts, they're beautiful purple color. All right, when we do a delta in chemistry, we've talked about this before, but we want to continually bring these back. It's always final minus initial. There's one exception that we'll come across this year and not till next semester. So we take 50.8 minus 45. Plus, it's illogical to have a negative volume for the amethyst. So that gives us a volume of 5.8 milliliters for our amethyst. Now we want to plug that into, substitute into the density formula. So we'd have density is equal to our mass, 15.28 grams, divided by our volume, 5.8 milliliters. Now, normally you would report a stone in centimeters cubed, a solid, but we displaced water, so milliliters is a valid unit, and we would get 2.6 grams per milliliter, or you could say 2.6 grams per centimeter cubed. Now, I'm reporting this to two significant figures because our subtraction, in the context of our subtraction, we actually ended up with 2. If you were to have to do this on a test or a quiz, we would allow you to still go by the fewest numbers from your givens because we didn't make you learn the sig figs for addition and subtraction. Now, a couple more key points. You have to memorize the density of water. It's the only one you have to memorize. It's 1.0 gram. Remember, if we have a slashed unit, we can set that up as an equality, is equal to 1 milliliter. We're going to find that not only can we use the formula for this, but because we have a slashed unit, which we can set up as an equality, we can also use density in a dimensional analysis equation if we want. And we can flip-flop it at our convenience. Grams on top or milliliters on top, depending on how we're converting. Now, this is only true at 3.98 degrees Celsius. The density, since it's mass over volume, right? If you increase the temperature, you're going to change the density because volume will change. But for now, we're just going to let you continually round it to 1.0 grams per ml, and you would be told what it was if it was something different than that. Now, the activity that we're going to do will demonstrate this last little concept very well. Substances that are less dense than water will float. If they're more dense, then any substance, they'll sink. So the most dense is going to be on the bottom, is going to be the most dense, and on the top, you're going to see your least dense. So in this case, we have a substance that's 3.2 kilograms per 1950 mLs, and we want to know, is it going to sink or float in water or mercury? So let's do a calculation to compare. Remember, you can list your givens or circle your givens, but we need to check our units. The density values we know are in grams, and the mass given was kilograms. So we need to convert kilograms to grams before we can plug into our formula. So it's 3.2 kilograms. I want to get rid of kilograms, put 1 by the prefix, 1 times 10 to the third. If you don't set it up, I've seen students do it time and time again, they move the decimal in the wrong direction. So I would strongly suggest setting it up. I'm now going to plug it into my density formula. 3,200 grams divided by 1950 milliliters is 1.6 grams for every milliliter. Now, in this case, I'm not so worried about what the density is because the question asks us, will it sink or float? Well, this number is greater than 1, so it's going to sink to the bottom if there's water present. But it's less than 13.6. And that means it's going to float on top of a column of mercury. And I really like this lab that's been developed. Mr. Coder did a lot of work on this, and it's a fun lab, and I really think that it will firm up these concepts quite well. That's it, folks. This is our last video. We got to be checking your notes to make sure you did your notes, and we will work on more problems.